The math, like the mechanics of the math with polynomials. So far, we've done rates of change mostly with polynomials, and it's kind of like it all worked out the same. So when we did that back in Unit 2, you got familiar with how things tended to always add to 0. Like that's kind of how it had to work out, and you knew that. You might have sort of forgotten that, but at the time you knew that, like you were expecting your constants have to add to 0. So some of that's similar, but then there's also some differences when we're doing rates of change with rational functions. So like the mechanics look a little bit different, okay? But first of all, like the average rate of change is always kind of the same. So how do I do average rate of change? This is like, if you picture the graph, we could graph that f at x equals 4 over x plus 2. We could graph that, and then f at 2 and f at 8, that's 2 points. Right? So I've got 2 points on the graph, and I'm looking at the rate of change between them. What's the change vertically? What's the change horizontally? That's all we've done, right? So first of all, let's do f at 2. What does that work out to? Works out to 1. 4 over 4. And then f at 8. 4 over 10 or 2 over 5. Okay, so the change in y's over the change in x's is like f at x2 minus f at x1 over x2 minus x1. So if I call f at 8, if I call that x2 and f at x2, I get 2 over 5 minus 1 over 8 minus 2. So that's negative 3 over 5 over 6. It's actually worthwhile. You could do this on your calculator for sure, but it's actually worthwhile for what's coming next to take a look at like I wouldn't normally show this step, but how would you actually do this division? Negative 3 over 5 divided by 6 over 1 is negative 3 over 5 times 1 over 6. So it's negative 3 over 5 times 6, which is 30, negative 1 over 10. So like when I'm dividing a fraction by a whole number, the whole number just joins the denominator, multiplied into the denominator, right? And that's why, but it ended up being negative 3 over 5 divided by 6, so I did 5 times 6. And that would always happen. If there was a fraction in the denominator, then it wouldn't quite work out that way. It'd be a little bit different. But in this case, that's what it works out to. So that's like the slope of the line between those 2 points. Makes sense that it might be small. Imagine what these different graphs might look like. Maybe that's f at 2 and that's that's 8. Not going to have, like that's negative, and it's not going to have a big slope. It's going to have a really, really shallow slope, right? So that makes sense. That'd be interesting. What would happen if you were finding the rate of change between those 2 points? Remember we talked about this. We said when you find the average rate of change between 2 points, you lose any sense of what happens between those 2 points. You're just talking about where it started and where it ended. Did I drive straight to my destination, or did I make a whole bunch of turns and other stops along the way? Average rate of change ignores all that, and in fact, could even ignore an asymptote. Average rate of change between the two, except there was a value that didn't even exist. That's kind of interesting to think about. Okay, so average rate of change, that's like grade 9 question. y2 minus y1 over x2 minus x1. Don't forget that. That's easy. People forget it because we don't do it a ton. But what I do want you to remember, I'm sure I've said this before, is understand the difference between average rate of change and instantaneous rate of change. Really understand the difference. Okay? So here we go. Find the instantaneous rate of change for the function above at x equals 3. So the function above is f at x equals 4 over x plus 2. So first thing, we want to know the value. F at 3, 4 over 5. Is it possible the average, so 3 is within the interval that we just checked the average rate of change of, right? That's in that interval. And that had a negative rate of change, so a negative slope of that. That's a secant line because it crosses through 2 points, right? So the line that connects those 2 points we call a secant. Is it possible that had a negative slope? So will this have to be negative? Sam, you're saying no. Why do you think?
It doesn't necessarily have to be because, as you said, it can believe more stuff like asymptotes. But like this, because there's almost the shape of the graph.
Okay, very nice. So in general, it doesn't have to. Every point within the interval of, let's say, an average rate of change that we found doesn't have to share the same sign. Because within an interval, if we're looking at a polynomial graph, the graph may have gone like this, which all those different points will have positive or negative, like it'll flip back and forth. And that could happen several times within an interval, right? So absolutely, instantaneous rate of change does not have to share the same sign. So this may work out to be negative, may work out to be positive. However, if you graph this even in your head, or like if you thought about the actual graph, you would probably know if it will or not, right? Like you could get a sense of what it looks like and what kind of a sign it'll have. Anyway, it's not really, it's just something to think about, just interesting to think about. So let's see. Slope of the tangent equals, limit as h goes to 0 of f at x plus h minus f at x. X is over h. X is 3 for us. So 3 plus h or h plus 3 might be a little bit of an easier way to do it. Okay, so now I sub into f at x. So 4 over h plus 3. 3 is my x, right? Plus 2 minus 4 over 5 over h. So the red part is my f at x plus h. I took x is like, this is where at x equals 3, right? That's what we're finding. So I put 3 in for x and x plus h, or h plus x. Sub that into x of that original function. All right, let's do some work. So I'm going to need to do some common denominator stuff here. I'm going to simplify first, so I'll do it step by step. H plus 5 minus 4 over 5 all over h. Okay, so I'm going to multiply this by 5. And multiply this by h plus 5. We're getting a common denominator. All over h. Don't drop that. Maybe it's a pain, but you got to write it on every line. Okay, so I get 20 minus 4h plus 20. So see how that worked out? The constants are still going to add to 0. Looks a little bit different, but that should still happen. Over, and I'll do this in 2 steps. H plus 5 all over h. Remember what I told you about denominators in that last one, right? So this is like I got a fraction divided by a whole, like h. H is going to 0 in this case, but it could be a fraction, but it's a single thing. So what's it going to do? It's going to join the denominator of the top part and multiply. Does that make sense? You could do this in 2 steps like we did above, or in a few steps, but what I'm going to do, okay, so if you want to put your pencil down and just watch for a minute, like just so you can follow along, don't let me go too fast. 20 minus, that should be minus. Sorry. Right, because it was minus all of that. So 20 minus 20 is 0. So I'm left with negative 4h on top, and then I'm left with h times all of this. And I'm going to expand that, 5h plus 25. And you probably want to just leave the h out front, because otherwise what we would do is we'd multiply it in and then we'd factor it back out so that we can do this. Remember how that's the whole point? Like that's what we're doing. We can't divide by h because h is going to 0 until I do some moving around. And now I can sub 0 in for h. So that means this equals, well, I'll write this out again. 5h plus 25. Come up over here. Whoops, equals limit. Now I can put 0 in for the h. The h is on the bottom, but that's okay because there's other junk down there too. So equals, so this is going to be gone. Negative 4 over 25. And that's it. There's my slope of the tangent. That's it. That's all there is to it. The common denominator stuff is similar to what we've been doing. Like all that work on in the numerator is similar to what we've been doing. But it does probably feel different from the other polynomial rate of change stuff that we've done, and it's a little bit bigger. I have a question. Any thoughts or questions about that? Yes, Russ.
How do you just get rid of the 5h on the bottom?
So that's when, so all along here, I can't put 0 in for h. Remember, we want h to be 0 because it's x plus h. When h is 0, it's the slope of the tangent at that point.
Yeah.
But I can't put 0 in for h here because then I'd be dividing by 0. And I can't do it there because I'm dividing by 0. And I can't do it there because I'm dividing by 0. But down here, I can. I can put 0 in because now I got this 25 sitting here too. So once you can do it, then go for it. We don't need our limit statement anymore because h is gone because it's 0 now. And we worked it out. All right, let's try another one. That was too easy. Let's make it harder. So 2 minus 2 over 2 plus 4 0. Zero over 6 is 0. There's nothing wrong with that. We're just finding the instantaneous rate of change at an intercept. Right? 2 makes the 0, the top 0. So that's an intercept of that function. And we're going to find the rate of change at that point. Intercepts have rates of change as long as they exist. Nothing wrong with that. Make the math a bit easier maybe. See how it turns out. Because I'm going to be subtracting 0. Okay, see if you can come up with the original statement. So I'll write the formula down. See if you can sub in properly. Did you get that? So the red part's my f at x plus h. It was x minus 2, so I put h plus 2 in there. And it was x plus 4, so h plus 2 plus 4. Is that okay? H plus 2 minus 2 is just h over h plus 6 minus 0, so that's gone, so all over h. So yeah, look at how that ended up actually being quite a bit easier. So h is going to join my denominator. And then I can divide those. Of 1 over h plus 6, which equals 1 over 6. Is that okay? Questions, questions, questions? Yep. Oh, that's it. We're done. So I'm going to let you do some practice, and then we might do another example that's even a little bit harder together on Monday. None of you are listening to me because you're busy reading what the